So today, and I'm hoping my pen works today. Yeah, it looks like it is. Okay, good. So solving exponentials is the title for today, folks. And yesterday I told you that I wanted to draw something, so I pre-drawed it. And if we had been in class, I would have forced you to draw that too. This is dragon to the sheep equals dragon to the question mark. If you have the same bases, that means the two exponents have to be the same, so that means question mark equals sheep. So that's basically the idea that we're using here, okay? So yesterday I started to show you an example of this. I'm going to just do another basic example to get us started here. So what we want to do is we want to have the same base on both sides. So 4 to the power of what equals 64? Does anybody in chat have the answer? Correct. So the answer here would be x equals 3. We would just drop the bases at this point and get x equals 3. Okay? So just as an aside, we probably all know a lot of our powers of 2, but how many of you know or are comfortable with your powers of 3? Because if you are comfortable with some of them, as well as some powers of 4, you might be able to quickly start recognizing some of the answers a lot faster. So 2 to the power, and I don't know them all. I don't know, I'd have to calculate 6 to the 3 and 7 to the 3 and anything beyond, but I do know them at least up to 5 to the 3. So just to fill in the note here and get you to see it, 2 to the 3 is 8, 3 to the 3 is 27. Please correct me if I make any mistakes here. 4 to the 3 is 64. 5 to the 3 is 125. Now 6 to the 3, so you know, how quickly could you calculate that in your head? And I just want to show you a little trick, and some of you might know this already, for calculating bigger things in your head. We know 6 to the 2 is 36, right? So we want to do 6 times 36. Now, one way that I feel that's a little bit better, and I know some of you know the answer, but just in case you had to do this on your own, one thing that I discovered recently is that if you break this down into 30 plus 6, you can use distributivity to do these kinds of calculations in your head. So 6 times 3 is easy, and 6 times 30 therefore just adds a 0, right? So that would be 180. And then 6 times 6 is 36. And then you just add those two numbers together. So this is a technique, I don't know if you all know this, but it's a very powerful technique for distributivity. Now, some people might struggle adding these two numbers, but one interesting way of adding, and I know that elementary schools teach adding from left to right, but you can actually add from right to left. 100, this is 1 means 100, so that's 100. 8 and 3 is 11, but we have to add a 0 because it's actually 80 and 30, so 11 is 110, and then 6. And then 100, 110, and 6 is a lot easier to add in your head than trying to carry numbers. I mean, this one's not that hard, but sometimes they're a little bit harder than that. So I'm running out of room here, but we'd have, and again, I just add from left to right instead of right to left. So 216, right? So that would be that one. And 7, I'm going to trust is 343 from what I'm reading in chat. Okay, now, like I said, I know very comfortably up to 5 to the power of 3. Beyond that, I don't know them very well, probably because textbooks don't usually go much higher than this, you know, simply because you're starting to get just, you know, bigger for really no reason. You can understand the concepts just with looking at some of these. So with powers of 4, and I'm going to let you fill these in yourselves, folks, with powers of 4, you know, same thing. If you just practice a little bit with your powers, just to get to, and you're going to see some of these pop up throughout the work that I'm going to be giving. So eventually, hopefully, you'll start to get comfortable with them if you're not already comfortable with them. Okay, so going to a slightly more complicated example now. 2 to the x plus 2 equals 8. So the whole idea is we want to have a common base on both sides. So 2 to the x plus 2 doesn't change. We need to write 8 as a base of 2. And, well, looking up here, we see that that answer is 3. And now I drop the bases. This is a logic step. We're not dividing by 2. We're not subtracting by 2. We're just dropping the bases because drag into the sheep equals drag into the 3, which means sheep equals 3. So x plus 2 equals 3. And we subtract 2, which gives us 1. Okay? So the concept, if you understand the idea that we're just changing 8 into a base of 2 to match the base that's on this side, that's pretty much the whole concept. So I'm just going to pause for a second. Are there any questions at this point? Okay. So here's and I'm going to jump a little bit here because I think you can handle it in difficulty level, especially since some of you have already seen this stuff before. Now we've got some slightly more complicated exponents here, okay? So how do we deal with that? Well, we've already got pretty much our lowest base on this side. So we've got to change our 27 into a base of 3. So this side stays the same. If I change this to a base of 3, as we've seen before, that becomes 3 to the power of 3. Okay, so 27 has been replaced by 3 to the power of 3. And the power hasn't changed on the outside yet. Oops, wrong color, sorry. So I have to combine these two, and I was thinking yesterday as I was planning this lesson, normally we would have started with the exponent rules, but from what I remember talking about in class, some of you have already seen the exponent rules, and I feel like you should be fairly comfortable with this if you've seen them at all. In case you haven't, this is a power of a power. So somebody in chat, can you answer this question? Anybody can, throw it out there. When you have a power of a power, what is the rule for combining the two powers? That's right. So we have to multiply these two, okay? Now, the problem is this is an entire one thing. So technically you should really be considering this to have a bracket around it. Which means, and I'm going to move this over to the side just for a second, this is basically a distributivity scenario. So those two things have to multiply following the distributive law, okay? So what's going to happen, sorry, I'm just going to move my phone off the table so it doesn't make any noise. So what happens here is we have 3 to the 4x equals 3 to the 3x plus 9. And now we have one base, one exponent, one base, one exponent on both sides. And this is where we can drop those bases. So we're back to just doing common algebra at this point to be able to solve that exponential. I had to cough there, so I hope that time I was able to actually mute the mic. So now we just have to isolate, and this is simple algebra. We're going to bring the 3 over to this side, which is really nice because subtracting by 3 just gives us 1x. And then we're going to have the 9 on this side, and that's our final answer in this case. So, slightly more difficult because of this distributivity, but these are all skills you already have. So I'm hoping that that's pretty self-explanatory. Now, what happens in a case like this? Now, I know some of you already know about logarithms, but we're not using logarithms yet, okay? So this is a case where I can't change the 7 into a base of 2. So for now, what we're going to have to do is use a guess and check method, okay? And with this guess and check method, the key is when do we stop? So 2 to the x equals 7 means I have to do 2 to the power of something to get 7. So I'm going to switch over to the calculator here for a second. And the calculator wasn't working this morning, so I'm hoping it is now. Looks like it is. Okay, so 2 to the x equals 7. So we know that 2 to the power of 2 equals 4, and 2 to the power of 3 equals 8. So our exponent is somewhere between 2 and 3, which means it's a decimal. Okay, so yes, you're guessing. Now, that's great. That's what we're supposed to do. I just want to show you what could happen if a student, and it's the 2.7-ish that I'm talking about specifically here. If we go 2 to the power of 2.5, we get a number that's too small. Okay, 2.5 is between 2 and 3, but the number is too small. So I'd like to suggest that a good technique is to always have the difference. So if 2.5 is too small and 3 is too big, what is the halfway point between 2.5 and 3? It would be 2.75, right? So 2 to the power of 2.75, and we're closer to 7 now. We're much closer to 7 now. So if you keep having the difference of your decimal values, it's a good way to get as close to the answer as possible in a very, very logical and I guess good order of steps to follow. And I believe there's an actual name for that kind of, it's kind of like a type of sorting that you do. Okay, so how close can we get to 7? So, and I'm not going to do this for too long, but I just want to show you that there's a rigorous trial that you have to do here. So somebody's suggesting some numbers, but if I have the difference from 0.75 to 1, that's 25 divided by 2. No, that's 12.5, right? So I'd be going to 2.855. Anyway, whatever. I don't have to be perfect. Thank you. 2.875. I'm trying to do the math in my head here with decimals. It's not that easy. So if we go 2 to the power of 2.875, so now whoa, did I make a mistake there? Oh, I did. I did a double 2. Sorry about that. 2 to the power of 2.875. Whoa, what's going on? There we go. So that one's too big, okay? So 2 to the power of 2.8 would be probably my next try. And now I'm not going to do the halves anymore because I know that I'm very, very close, okay? And I know I'm probably just, belaboring the point here, but I just want to show the rigorous nature. So now we're really, really close to 7, okay? How close is close enough, right? So it really depends on the type of question you're being asked. We could go 2 to the power of 2.805. Like, I know we know an answer better, but so how close is close enough? So usually these questions, if you're within, a precision of like 3 decimal places, I guess precision might be the wrong word there, but like this number 6.988 is definitely going to round to 7. Okay. So, and some students I've seen on tests will try like 10 different, it's called a bisection search. Oh, cool. I wasn't sure of the term. Thank you. Remember, I studied math and French, so my terminology going back sometimes is a little bit different. But anyway, and I'm old. So how close is close enough? Okay. So I would say that, somebody said 2.81 is good. I'm going to use that answer as the answer for here. Let me switch back to that scene. Okay. So x would be equal to 2.81 through rigorous checks. Okay, so for right now, that is the method we're going to use for these kinds of scenarios. It is, I still think this is fun to do, in my opinion, because it trains your mind to think about what's the best next step to take. So until we learn about logarithms, that's the way we're going to do those kinds of questions. I noticed, side note here, I noticed when I was editing my videos that I tend to speak fast online. I'm going to try to slow that down a little bit. It's probably because I've been quite nervous doing this, so bear with me. We're all learning this stuff. Okay, so let's look at some more difficult examples. Negatives tend to throw people off, and part of the reason why is because in our recent lessons about exponentials, we talked about the fact that you're not supposed to have a negative base. You can have a negative base, though, theoretically, mathematically. So you still need to be able to algebraically solve questions that have a negative base, even though technically they're not a graph of an exponential. Okay? So now only special cases will work. This one is one of those. And I'll explain, if I remember, I'll explain what I mean by that in a minute. Can we change negative 125 to be a base of negative 5? That's right. Now, this side doesn't change. I would ask you to think of why we can do that here. And maybe even think about why, what would be a condition or a scenario where we, what would be a scenario where we couldn't do that? Yeah, so let me ask you this. What would be one thing that I could change on the right-hand side that would make this question not be able to be answered? A small thing. The negative where, just to be clear? Definitely losing a bracket would make this unsolvable as well. Yeah, that's another thing that could happen. So, correct. That's what I was looking for. This negative right here, if that negative wasn't in front of the 125, if it was outside of the bracket, if it was a positive, and in fact, even losing the bracket would cause that to happen as well. We wouldn't be able to solve this question because there's no way of writing a positive 125 as a base of negative 5 because we need it to be negative. The only kind of power that'll give us a negative is an odd power in this case. So, perfect. That's the kind of thinking I'm hoping you're doing all the time when you're looking at questions like this. You know, that deeper kind of understanding of what's going on. So, awesome. So we can now solve this one. Now, folks, I normally do get my students to write out every step, but you folks are a little bit stronger at math. I'm going to drop the bases now, okay? And at the same time, I'm going to do the distributivity, all right? Just to save us a little bit of writing. So 2x is equal to 9x minus 12, okay? Did I make a mistake there? Okay, thank you. And now we just isolate. And yeah, no problem. Hey, you saw the mistakes I made yesterday. It happens. So So now we want to isolate x, and it's better to bring the 2x over to this side because we're trying to get positive x values. So we're going to get 7x is equal to 12. I believe I did that right. And then our final answer would be 12 over 7. Now, please be careful. A lot of people will mistakenly write 7 over 12. I don't know why. It just happens. Okay? So, so that should be the correct answer, I believe. Okay? So I'll pause for a second again. And some people were saying they were getting a little bit of lag yesterday. So I'm going to give everybody a chance here to ask any questions about this one, because this is a little bit more difficult one. So are there any questions about this example? Yeah, let's not troll people for their grammatical errors. Only I'm allowed to do that. I'm the teacher. Are there any questions about this problem that you'd like me to explain in more detail? I'll give you one more second. Okay, time's up. So let's keep going. Having a little bit of trouble scrolling down with my pen here. Let's see if that worked. Oh, it did. Okay, so what about this guy? In chat, can somebody say what would be the first and best step to start with here? Anybody? Before changing the base, there's one other thing that we should do. Okay, let me ask this question. What is the base on the left-hand side? Ah, now you're starting to see it, okay? There is no bracket around that negative 4. That means this negative is technically not attached to that 4. It's attached to the whole thing. That means that negative is like a negative 1 multiplying this side. And so is that negative. So the very first thing we should do is get rid of the negatives. Okay? And I want you to compare that question to this one. Why weren't we able to get rid of the negatives up here? Well, because the negatives are part of the base. That's what the bracket is showing. Here, the negatives are not part of the base, and it's very confusing, okay? Like I said before, some of your calculators don't even get this right. So the very first thing we want to do is factor out the negative 1, or just divide by negative 1 on both sides, right? Or multiply by negative 1, however you want to think about it. With negative signs, it's easy to get rid of them either way. So that's the first step that we should be doing here. And we can only do it because there's no bracket around the bases. Now we can change everything to a base of 2. So we've got 2 to the 2 to the x, and 2 to the 3 to the x plus 1. And then we can just do our distributivity on this side and multiply the 2 powers on this side. So 2x is equal to 3x plus 3. And you folks can finish that one off. Okay, so the answer is already in chat. As a, do it quickly in your head here, and you'll see what the answer is. Okay. Yeah, no worries. Okay, so next step. Here's a tricky one. I'll give you a few seconds to think about it. When is this true? And there are more than one answer. X equals 1 works, but there are other numbers that work. So I'll do that off to the side here. Negative 1 to the 1 is definitely negative 1. But what is negative 1 to the 3? What is negative 1 to the 5? Okay, that's correct. So this is all odd numbers are a possibility. Yeah, so x does not equal 2n. 2n is a subset of z. Oh gosh, I can't remember. I would accept just all odd numbers. So x is an element of all odd numbers. Oops. Again, forgive my writing here, folks. I've explained that it's not easy to do this off the tablet. But isn't 2n minus 1 the... And this might be something you may have seen in your independent study. Isn't 2n minus 1 the way that we write a set of all odd numbers? N would start at 1, right? So I think we can write that as our odd numbers. And I'm sorry, folks, I actually didn't look this up previously, and I don't know the exact notation because we have to say that n starts at 1. Yeah, n starts at 1. But, oh, yeah, n is greater than or equal to 1. Duh. Right? That would make it work. But it would have to be integer numbers only. So we'd have to state that n is integer numbers only. Yes, correct. So anyway, there is a notation for that, and I if I'm not mistaken, I could be wrong. I think somewhere in your ISU they talk about that. So let's write. I think the element. I think integers is z. I think. You know what? I'm not going to write it down just in case I'm wrong. Yes, it is. Okay. I'm going to trust you on this. If you're wrong, it's Zinger's fault. Okay, but I'm pretty sure when you say n is an element of z, that's stating that n is an integer. Is that positive integers, though? Okay, you know what? Just in case, let's just do this for now, just because I'm not sure. Yeah, so I'm not sure what the notation is for all n is all positive integers. Okay, you know what? Let's just leave it like this for now. Okay, just to be sure. So. Let's move on to this guy. Oh, maybe just to come back to this question. I got really distracted there. Yeah, so you may have questions, folks, that have multiple answers. So you've got to actually think a little bit more about how you're going to answer it. So just be a little bit careful, okay? There's one of these in your textbook. Actually, there's 2 of them in your textbook. So what about this guy? So, now there's fractions. Our favorite part of math, fractions. I'll give you a few seconds again to think about this one. I'll give you a hint. Is there a way to change this into the same base that we would change this? So the answer's already been put in chat, which is great. We need to flip this guy. This guy is a fraction. This one isn't. We need to flip this guy. What flips a fraction? Well, negative exponents flip fractions. Right? So if I write this as 5 to the 3, oh, sorry, I'm thinking of the other side. 5 to the 2 to the n plus 2. I can write this base as was stated, as 5 to the negative 3. Because 5 to the negative 3, well, 5 to the 3 is 125, but we need to flip it, and the negative exponent does that. And now we've got our similar bases. Okay? And once again, not going to solve this one fully, folks. That's something you can do on your own time. You might even be able to do it in your head here. See if you can follow along. 2n plus 4 equals negative 3n minus 3. So I'm going to have a 2n on this side and a negative 3n on this side. When I bring them together, that's going to be a 5n. I'm going to have a 4 on this side and a 9 on that side. When I bring the 4 over to this side, it's going to be a 5. If I'm not mistaken, that's 5n equals 5 and n equals 1. So, you know, just a little bit of mental math exercises this morning. I would want to see the steps, at least a few of them, okay? But I think that's right. And you can correct me on your own time for this one, because I did try to do this one in my head. I'm going to pause for a second. Are there any questions about this question or the one that we just did? I'll give you another 10 seconds for questions. No mistakes either, I hope. Okay, let's move on. What about this guy? I'll give you one hint here. Careful with your selection of base. What base should I use? Is there another option besides what was just typed in chat? Is there another option besides what was just typed in chat again? I like that option better. Can we use 100 as our base here? You don't have to go to the smallest base. It's not wrong to do that, right? But look at how many zeros are in 10,000, right? Isn't 100 times 100 10,000? So if we go to 10, we're going to have to distribute that. We're going to have to distribute that into here. I mean, it's not that big of a deal, but if we can find a quicker way of doing it, we might as well, right? So wouldn't this be 100 to the negative 2 equals 100 to the y minus 2? And now I can just drop the bases immediately without having to do the distributivity. It's not wrong to go to a base of 10, but in this case, my personal preference would be to notice that I can actually just use the base of 100. Okay? Are there any questions about that? And here's an interesting scenario. We ended up with y equals 0 in this case, right? And I guess, now that I look at it, guess and check would have answered that question pretty easily as well. But anyway, this exponent won't always be that easy. My point was, take a look at your bases. In this case, the denominator's base value could be changed directly into 100 instead of going to 10. That's all I'm suggesting here. The other way is not wrong. 10 base wouldn't have lost any marks or anything, but you know, speed does become an issue at some point. Okay. What about this one? You can probably tell by the tone of my voice there's something fishy about this one. Let's start with the base. I think everybody can tell me, well, I hope everybody can tell me what the base for this one's going to be. Does 8 work? Does 4 work? Do we have to go to 2? Four to the what equals 8? Careful. Oh, were you giving me a power there? Okay, I actually don't have my calculator right. Oh, I actually do. I don't want to check, though. I'm pretty sure that the only base that works in this case is a 2. I'm pretty sure. It is 2, right? Like 4 to the nothing gives 128. 4 to the 2 is 16, so that doesn't work. I'm pretty sure it has to be a 2. So we're going to do 2 to the power of 3. X squared plus 2. Okay, and I'm trusting you here. Is it 2 to the 7? Just give me a yes or no. Yes? Okay. That's 2 people saying so I'm going to trust you. Right? Okay. Let's drop the bases and do the distributivity at the same time. Okay? So we're going to get 3x squared plus 6 equals 7x. Why am I writing uh-oh? How do we solve this? Correct. You cannot solve it in your head. What do we do to solve it? Before we factor, what kind of equation is this? Yes. This is a quadratic. You cannot solve a quadratic the same way as you solve linear scenarios. What do all quadratics have to equal to before you solve them? Correct. So we've got to bring everything over to the same side. You're not going to like me for this one, folks, by the way, but I don't care. It's great. It's an awesome little learning experience here. Okay? All right. Try to factor it. Well, maybe this isn't the example I was thinking of. I might have been trolling you for the wrong reason. No, I think I'm right. I made this one significantly harder. Correct. If I put a 9 and a 2 here, I almost made the mistake myself. 9 would have to be negative, but that doesn't work. So this doesn't work. Okay? Negative 9 times 2 is negative 18. Yeah, wrong signs. I almost made that mistake too. That's why I was doubting myself there. But I'm pretty sure I had chosen one that's not factorable, so you can't factor. If we can't factor, folks, what is the most efficient way to solve a quadratic? Solve a quadratic when you can't factor. That's right. So we actually need the quadratic formula here. Okay? Which I'm going to do with you because something even meaner is about to happen. So first thing about solving the quadratic formula is using your discriminant, right? To find out if we have real zeros or not. So b squared is 49 minus 4 times a, which is 3 times 6. So that's going to be 49. 12 times 6 is 72, I think. I'm just going to do my calculator off screen here. And 49 minus 72 is negative 23. Yep, you got it. This is a complex number scenario. What did I just say? Minus 27? I had some technology issues there. Minus 23. Sorry, folks. Yeah. So we have complex scenario here. Now, yes, normally that means we can't solve it when we have a discriminant that's negative, but we can solve it. I showed you before the March break, an example of what to do. And what we're going to do is we're going to write this as 23i squared. We're going to replace negative 1 by I squared, okay? And it's this fancy little I here, all right? And we are going to solve this. We're going to find the two complex roots, okay? Just to show that it can be done. So the full quadratic formula, we're finding our x zeros here. I like to write the subscript zeros. I think I've mentioned this before just to show that we are finding the zeros right now. So without writing the entire formula for the quadratic formula, let's just fill in the numbers at the same time. So it's minus b plus or minus the square root of b squared minus 4ac over 2a. So minus b would be 7 plus or minus the square root of 23i squared, all divided by 2a, which would be 6. Okay, I'm going to put a little dot here to show that that's a multiplication times I squared. That gives, when you have the square root of two things that are multiplying, you can pull out each square root individually. Now, 23 doesn't root nicely, okay? So we're going to write plus or minus I square root of 23 over 6. And the further along in math you go, folks, the less you're going to want to write decimal answers. So technically, that would be your final answer here, okay? You could split it off into your two separate ones, 7 plus and 7 minus. I'm not going to do that. You can clearly see that there are two answers here. But when you have a complex number, meaning a square root of a negative number, you just change the negative to an I squared, and then you can continue going as normal. You would just state that these are imaginary roots, and as somebody's already stated, that basically means the quadratic is... I believe this one is above the x-axis, yes, because it's a positive a value, which means it's a opens up or smile shape, okay? So I really like that question simply because it pushes us to use a lot more knowledge than just what we've been doing. So this is a scenario that's a quadratic. And I hope everybody was able to follow that without too much trouble. I think I have at least one more slide, and I was planning on ending with this slide. I even put myself a reminder here that this might be the last page here. There are two more different questions. I don't think I'm going to have time to do both today, and we've already done a lot, so I don't want to overwhelm you either, and there will be some homework questions to try. But I'd like to maybe start introducing this one to you. And the reason this is one of the hardest types is because we now have a subtraction between our two bases. And subtractions and additions are evil. They are the most difficult operations to deal with in math. And the reason is because they put a wall between the things that are on either side. And you can't add across that wall unless both things look exactly the same. Now you might say, well, sir, they do look exactly the same. They both have a base of 2. Their exponents are different. So just like you can't add an x squared and an x cubed, or subtract them, you can't subtract these two either. Okay? Now, I'm going to plant a little idea in your head here. This is actually a quadratic. And I'm wondering if you can see how this is actually a quadratic. I'm going to write it in a slightly different way. And it has to do with the fact that this came from something. We can actually split these apart. I can write this like that. And as soon as I do that, this equation now has a power of 2 in it. And as soon as you have a power of 2, that usually means that the equation is quadratic. Okay? And you are right. We are going to use the technique of variable substitution here. It might be hard for you to see that this is a quadratic. So why don't we set 2 to the x temporarily equal to big X? And this is the every time I did variable substitution all the way through university, and it's been a long time since I've been in university, I know, but they always use a capital letter, or my teachers always did anyway, to represent the variable substitution. It's to make you remember at the end that you're not done once you've solved the quadratic, and I'll explain that in a minute. But I'm going to replace this 2 to the x by a big X, this 2 to the x by a big X. This becomes x squared minus x, and I'm going to bring the 48 over to this side at the same time. And that is now temporarily a quadratic. Okay? Now, if I remember correctly, is this quadratic factorable? It's not coming to me right now, folks. Can somebody help me out? I'm pretty sure this is supposed to be factorable. It's not factorable? Does 3 go into 48? Let me do some quick math here. 3 and 16. 4 and 12. I thought I had made it factorable. No, it's not. Okay. I would like it to be factorable. So, if we change this to, sorry folks. Okay. What could we change the 48 to make it factorable with a -1 in the middle? I'm just going to change it on the fly here. 42. This was 6 times 7, right? And yes, I just switched to French for a second. That's how I learned my timetables. Right? 6 and 7 is 42, right? And that gives -1. Okay. I think that's right. So here's what we would do. We would factor this normally. So we'd have a big X here and a big X here. And this is a type 1 quadratic. So in a type 1 quadratic, you can just plug those numbers in to the brackets. Like so. So I'm just going to pause for a second here because I know I messed things up. Are we all good to go here? Okay, good. So we got to this point, right? And now normally we would find our zeros, which we are going to do. So x would be equal to 7, and x would be equal to -6. I want to change the color, sorry. I guess it doesn't really matter, but we're not done yet. And that's why the capital X is there. The capital X is to remind us, wait a second, we did a substitution. So now we have to resubstitute 2 to the X back in here. Like this. And now we have to solve those. Oops. Now, these, unfortunately, are going to have to be solved by guess and check. Now, there's something special about this one. Does anybody see what's special about that guy? Is there any way we can raise a power of a positive base to any power, especially a 2, and get a negative number? No. This cannot be solved. And that happens sometimes when you're dealing with quadratics, where one, especially word problems, one number doesn't make sense. So the only one that we actually have to solve is this one. Which I'm going to let you do. Now, we didn't do 2 to the x equals 7 just a while ago, did we? That would be ironic if that's what we did. Anyway, yeah, try to find the answer to that through guess and check. It was the one we did? Ah, great. Okay, so we actually... That's hilarious. Okay, yeah. So, wow, we did a lot of work today, which I don't know. I really enjoyed this lesson. Like I said, graphing is okay, but solving is where the fun, I think, really lies in math. Now, don't get me wrong. Graphing on Desmos with that speed, amazing. But solving with algebra is really good. By the way, just as a side note, if I go back to one of our previous examples, or one of our easier ones here, right at the beginning, I'll come back to that last page in a second. You can actually solve this by graphing. okay? If you graph each side individually, a graph of 4 to the x, y equals 4 to the x, and a graph of y equals 64, when would they both be equal? Yeah, but on the graph, sorry. I'm asking you to describe the graph, like what would be special about the graph that would tell us that we got the right answer? You know what? I'm just going to show you. Let's go to Desmos. I believe I have it ready to go. If I graph y equals 4 to the power of x, and I graph y equals 64, what's going to happen? Oh, somebody wrote the answer down. Good. Now I'm going to have to zoom out for you to see it. Look at what happens. 4 to the x is the red graph. Blue is y equals 64, which is just a horizontal line. And there's a point of intersection. So you can actually solve these very quickly with Desmos, much more quickly than I could when I was in high school, because we would have had to do this by hand, but it does actually work. I could see software like this revolutionizing. Yeah, it's cheating. You know what, though? Like, that's the thing about technology, right? Is at some point, sometimes it makes other things a little bit obsolete. The only reason I would say that I don't like this for our class and students who are planning on going to university in a more complex field is somebody had to program this to work, right? This all works with the math in the background. We don't see that, but it's there. So that's that's really why you're learning the algebra is, you know, any child can type in equations if you tell them what to type, but do they understand what's happening, right? So we're at a level now where we want to understand what's happening. We don't want to just do it. So let me go back to the last screen. There are other types like this, by the way, folks, that are even more complicated than this, but I'm going to wait for tomorrow to show that. We've already been streaming for an hour, and I realized today that I've already forgotten to record this, so I'm going to have to download it and re-upload it to YouTube afterwards. Anyway, so in your textbook on page 23, and I'm actually going to show the textbook on the screen in a second just to show you, there is access to the textbook on the Google Classroom, okay? You'll have to look for section 1.3. So if anybody didn't have their textbook at home, you can look at it up on the Google Classroom, okay? This is what page 23 looks like, and I'm just going to go there right now and show you what I'm talking about. So, oops, that's page 21. By the way, if anybody wants to see that harder question that I'm talking about, you can look at example 3 on page 21. Okay? So, I'm not going to belabor that point, though. Page 23. Oh, and key concepts. This one's not very detailed, but there's always key concepts in a textbook, which is good. By the way, folks, I do not like the fact that this textbook use A as the base variable here. I'm telling you that right now. This is not the convention in normal textbooks as far as I'm concerned. It should be B, but, you know, variables don't technically matter, but I like B to be base and A to be the same A as all of our other transformations that we've seen before, which would be in front of the exponential. Anyway, I don't want to get the textbook people mad at me, but that's my preference. So on page 23, I want you to look at all of these questions from 1 to 7 to 11 even. Now, you might not be able to do 11, and you might struggle a little bit with 10. And I'm going to post all of these things on the Google Classroom so you know exactly what questions to work on. There are a lot of them here. You do not have to do them all, okay? And but I would like you to do enough to master this concept. I've also, as an alternative, I don't know if it's going to be as in-depth as this, though. I actually have posted, I think it's coming up right now, actually. It's going to be posted to the MathSpace site where you have some questions you can go do there as well. Either or, I think these ones might be a little bit better, though. So you can mix and match if you want, okay? And there's some questions down here in number 19 that are much more challenging. They're much more challenging, so if anybody wants to attempt those as well. So I will be posting, sorry, I've got the hiccups here, these questions online. That's it for today's lesson, folks. So I hope you enjoyed that again. There seem to be quite a few people online again, which is nice to see. And I know some of you may not be able to join us every day, but if you can, every school day, that'd be great.